In this chapter, we're going to talk about how atoms bond. So we've built up with our atomic models, and we've kind of talked about the history of the atom. We just got done talking about the atomic nucleus and nuclear chemistry and radioactivity and all that good stuff. And now we're going to talk a little bit more about the electrons, because the electrons are responsible for how atoms bond together to form molecules and compounds. And the most important electrons are the highest energy, outermost, which are called the valence electrons. The valence electrons. So the valence shell is the outermost, highest potential energy shell. So for remembering our Bohr model of the atom, we have a positively charged nucleus with each of these shells coming out, and each of these shells represents a specific energy level. So let's say this one's 1, this one's 2, etc. So if I have electrons that are in the inner shell, that's one thing, and then if I have electrons in the outer shell, then these are my highest energy valence electrons, so my outermost, the ones that are further away from the nucleus. Okay, so the valence electrons are the ones that are responsible for chemical bonding, and they can either be shared, and if we're sharing valence electrons, we call this a covalent bond. Covalent, meaning co is sharing, like if you cohabitate with someone, then you're sharing a house with them. Covalent bonds means that we're forming a chemical bond because of shared valence electrons. And they can also be transferred. And if we're transferring electrons from one thing to another, so if I have fewer numbers here, it might be easier to just lose some, or it might be easier to gain some. So if we transfer from one thing to another, then this is going to form charges, and these charges then can be attracted to each other and form ionic bonds. So we're going to kind of focus on two different classes of bonds, and we'll get into more detail on both of those. But in this lecture, I want to focus on a model that we use and kind of the idea that we use to support and predict the bonding of atoms. So a couple new terms. Atoms and elements we've already talked about. They're kind of the fundamental unit of chemistry. Now as we're bonding them together, we're forming molecules and compounds. And molecules are more than one atom chemically bonded together. And compounds are more than one type of atom chemically bonded together. So the difference between the two is kind of subtle. They both are more than one atom chemically bonded together, but molecules could be the same atom. So, for instance, H2, if I write this compound name here, H2, this is a hydrogen molecule. There's two hydrogen atoms that make it up, and so they have more than one atom chemically bonded together, but it's not more than one type of atom. So this is a molecule. If I have water, for instance, which is H2O, that means that I have two hydrogens and an oxygen. It's still a molecule because I still have more than one atom chemically bonded together, but it's also a compound. Because I have more than one type. So what we're talking about in this chapter is how we form these molecules and compounds. And the way that we do this, the way that we model this, is using what is called the Lewis dot model. But in order to talk about the Lewis dot model, we have to talk about what is called the octet rule. The octet rule says that an atom is going to form a bond in order to have a full valence. So atoms want to have a full valence, and a full valence for most atoms is 8. Eight electrons in their valence. So that's hence the octet part. So the octet is referring to the 8 electrons, and it's really just kind of a guideline. There are some elements that don't follow the pattern, and we'll talk about them as we go. But the octet rule says that an atom is really going to try to do whatever it can to get to a full valence, and usually that means either transferring electrons, like we said, so that would mean gaining or receiving electrons, or it's going to share electrons in order to get to a full valence. So we need to figure out a way to model these valence electrons because they seem to be pretty important. And the way that we do that is with the Lewis dot model. It's also called the electron dot model. And the Lewis dot model is named after a scientist by the name of Gilbert Lewis. I have a little bit of a soft spot in my heart for Gilbert Lewis, who came up with the Lewis dot model. He also did some work on acids and bases, but a lot of the work that he did was on chemical bonds. He had his hands in a lot of different pies. But Gilbert Lewis I have a soft spot for in my heart because he was nominated, I think it was 35 years, for the Nobel Prize. 41 total nominations over the course of 35 years, and never won the Nobel Prize. So I have a little bit of a underdog thing, and Gilbert Lewis kind of falls in that category. Okay, so the way that we're going to do this is we're going to look at our periodic table. So if you don't have a periodic table in front of you, it would help to have one. And I'm going to take period 2. So if I take period 2, remember the periods are the rows. So I'm going to take period 2, and I'm going to take the elements coming from period 2, starting with lithium and the alkali metals, and then going to beryllium and the alkaline earth metals. And now, period 2 does not include any transition metals. It's over the transition metals. So when you skip over the transition metals, you end up at 13 or 3A. And so you end up with boron, and then you have carbon, and then you have nitrogen, and then you have oxygen, and then you have fluorine, and then neon over there in your noble gases. So this is my whole period 2. And if you look, and we talked about this before, in terms of the numbers of the columns that they're in, the numbers of the columns can be either numbered straight across, so it goes 1, 2, this one's 13, 14, 15, 16, 17, and 18. So there's 18 groups across on the periodic table, and 1 through 18 would be the way to do that. So you'll note that I didn't use 13 or 3 through 12, which would be our transition metals. But the other way to number these is with our A's and B's. And if we look at all of these guys, these are all A groups. Now I think it's important to know both of the numbering systems because the A groups here, which are your main group or representative elements, if you know your A numbering system, then you're going to know how many valence electrons there are for those atoms in these parts of the periodic table. And again, this is just going to work for the main group or representative elements. So columns 1 and 2, 13 through 18. So the number here in front of our A, 1, 2, 3, 4, 5, 6, etc., is going to give you the number of valence electrons or the highest energy electrons on that particular atom. And this is the way that we represent them. We take our element symbol and we put a dot next to it, and that represents my 1 valence electron. Now I have 2 in the second column, so all of my alkaline earth metals have 2, and so I can put my 2 on there like that. Now note that I don't pair them up on one side. I'm putting them on different sides to start off with. When I have 3, then they're going to look like this. 4, like this. Now 5, I've run out of cardinal directions. I kind of did them on west, north, east, south, etc. And I ran out of cardinal directions. So now that I have more, I have 5 valence electrons for nitrogen, I'm going to have to start pairing them up. So 1, 2, 3, 4, 5. So I have a pair on this side of my nitrogen and then 3 individuals here. Now I have 6 valence electrons on oxygen. 1, 2, 3, 4, 5, 6. So now I have a pair here, and 7 on fluorine. 3, 4, 5, 6, 7. So I have 3 pairs and 1 individual, and then neon, 8. Okay, so neon has 4 complete pairs, and this is going to give you some information about the type of bonding that it does, or in this case doesn't want to be doing, because the name of the game is to try to get to a full valence, and for most elements that's going to be 8 electrons. Okay, so let's talk about these 2 types of bonding in a little more detail, and then we'll get into some individual videos on each of the types for how we can use these Lewis dot structures. Okay, so let's start with our covalent. The way that we can use the Lewis dot structure to look at covalent bonds is because we're sharing electrons to try to get to 8. So if I take fluorine, for instance, fluorine is in our column 17 or 7A, and it has 1 valence electron that's all alone, and the rest of them are paired. And these pairs here that are already paired up, we can't add more electrons to. So these pairs cannot be shared, and they're called lone pairs. So we can't share these lone pairs, so there's 3 places where fluorine cannot bond, and 1 place, this unpaired place, where it can form a shared pair. So if I have another fluorine here that also has 7 valence electrons, then it would make sense, and I hope this color works, it would make sense that these 2 could be shared, and when I share them together, then they look like this. And I've rearranged my order here. The order of them doesn't matter. So I still have 3 pairs that are unshared and 1 in the middle here that's shared. So this 1 in the middle here that's shared is my covalent bond. And so if we are analyzing this thing, then the goal is to have a full valence. And so a full valence for fluorine, this one has 8 valence electrons, and now this one has 8 valence electrons because of that shared pair. So they both have a full octet, so they're both happy. Okay, so that's the way that we look at covalent bonds. Now there's a couple of exceptions to this. One that you'll run into quite a bit is hydrogen. So if I take hydrogen and fluorine, for instance, while we're on the same subject here. Again, fluorine has these 3 unshared pairs and 3 lone pairs, 1, 2, 3, and then the 1 place that it can bond. Hydrogen just has the 1 valence electron. Hydrogen is just 1 electron and 1 proton. So if I was to share these guys, then I would end up with a structure that looks like this. With the shared pair in the middle here. The shared pair in the middle is still my covalent bond. But now when I'm analyzing each one to see if they have a full valence, then my fluorine here has a full octet, right? There's 8, 2, 4, 6, 8. And hydrogen has 2. It doesn't have 8. But that's good for hydrogen. Hydrogen just has a 1s orbital. So remember that the 1s orbital for hydrogen is all that it has. That's the highest energy atomic orbital it has. And so the 1s can only hold 2 electrons. And so a full valence for both hydrogen and helium is going to be 2 electrons total. So hydrogen only wants 2, so it's happy. Okay, now the way that we can represent in Lewis dot structures, when we have a shared pair like this, then we can just represent it with a hyphen. So now this becomes this compound with the hyphen that represents my covalent bond. And I can share more than one pair. There are times when I would need to share multiple pairs in order to get to a full octet. Let's take oxygen, for instance. Oxygen is in column 6A or 16. So I have two of these lone pairs, two of these unshared pairs, and if I have another oxygen here, and I'm going to draw it this way intentionally, easier to see, then when I'm putting them together, so I want to figure out how oxygen bonds to itself, then I could share a pair here, and I could share a pair here. And now if I have two shared pairs between my oxygens, it's going to look something like this. So two pairs shared in the middle, and then two lone pairs, two unshared pairs. And now if I'm analyzing them, I say, all right, well, this one has, with the shared ones, 2, 4, 6, 8. This one has, with the shared ones, 2, 4, 6, 8. So they both have full octets. And now when I represent two shared pairs of electrons, now I have oxygens that look like this, with this kind of, it looks like an equal sign, but the equal sign represents two shared pairs of electrons, which is called a double bond. And the way that you would represent this compound then, it's not a compound, it's a molecule because it only has the same element in it, is O2. So O2 has a double bond between the oxygens because they're trying to get to a full valence, which in this case is 8. Now if we look at another example, down to the column 15 or 5A, then we get to nitrogen. Nitrogen has 5 valence electrons, so one lone pair, one unshared pair, and 3 individuals. And again, I'm going to draw it like this. The sides that you put your electrons on don't really matter. Where you start putting your electrons on doesn't really matter. There's never been a convention that I've seen that's really standard, but it is important to not pair them up until you reach the 4 on one on each side. So if I'm looking at this, and each of my nitrogens wants to try to get to 8, I could share a pair here, I could share a pair here, I could share a pair here. Now when I put these guys together, I have 2 nitrogens, 1, 2, 3, that have 3 shared pairs in the middle, and then I have my lone pair on each side. And if I'm looking at these guys overall, these 3 shared pairs and my 1 lone pair give me 8 electrons, so it's happy. 3 shared pairs and 1 lone pair, 8 electrons, so it's happy. So they both have full octets. And now when I'm changing them to hyphens, I can change the bond to where it's just a hyphen. There's 3 shared pairs of electrons. This is called a triple bond. Okay, so that's the way that we talk about and use our Lewis dot structures for bonding and how to understand the way that these things will bond to bond. They want to share electrons in such a way to where they can have a full valence. That's the name of the game. And I'll get into more detail on covalent bonds. There's a couple different types of them in a different video, so keep an eye out for that. Let's talk a little bit more about ionic bonds. Ionic bonds. So ionic bonds are bonds between charged atoms, or ions. So an ion is a charged atom. So this is with either a positive charge or a negative charge. And so a positively charged ion is called a cation. So the way that I remember this, is I really like cats, so I'm positive about cats, so that's a good thing. If you don't like cats, that's harder, but you could remember that cat ions are positively charged because cats have positively charged, so if that helps, that would be one way to remember. And then anions are negatively charged. Not to be confused with onion or anion, as I sometimes read when I'm looking at a cookbook. So anions are negatively charged. So if you have a cation that's positively charged and an anion that's negatively charged, the bond that forms between them is an ionic bond. Okay, so here's how this works. If you have something like sodium, if we look at sodium on the periodic table, it has atomic number 11. That means that it has 11 protons, and in its natural form has 11 electrons. Atoms are neutral. They don't have a charge on them normally. So unless they're under the right circumstances, atoms will be neutral. That's the way that they exist. Now, sodium, if it was to lose an electron, so if it was to transfer an electron away, then it would only have 10 electrons. But it's still sodium, so let's say that we're transferring an electron. It's still sodium, so it's still going to have 11 protons. That part hasn't changed. But when I lose that one electron, now I have 10 electrons. Okay? Now the reason that it would want to do this comes from its Lewis dots, or from its Bohr model of the atom. It does come from the Lewis dot as well, but let's start with the Bohr model and then we'll go from there. Now sodium, if I was to give you the electron configuration for it, is 1s2, 2s2, 2p6, 3s1. That's my electron configuration for sodium. And so if this is my first shell, and this is my second shell, and this is my third shell, then each of these numbers refers to my shells, right? So these 2 electrons are going to be in this shell. These 8 electrons, the 2 in the S and the 6 in the P, will be in the second. 2, 3, 4, 5, 6, 7, 8. And then the 3s, there's just 1 in the third shell. So if I'm looking at this Bohr model of the atom, if sodium wants to get to a full valence, okay, and a full valence is usually 8, it looks like it's going to be easier to lose this 1, and when I lose that 1, then I'm going to have 8 in this lower shell, right? So I lose 1, but I still have a full valence. It's probably easier to lose that 1 than it is to gain 7. So sodium then, when it loses this 1 electron, when it transfers this 1 electron, I'm losing a negative charge, but I still have the same number of protons, so the overall charge on my sodium is going to be +1. So because it's positively charged, the sodium became a cation. So here's my sodium, and I write it like this with just the charge here. And if the charge is just a +1, then we just do the sign. And we can talk about that a little bit more later. It's different if you have more than one charge, but there's my cation. Now if I have something like fluorine, fluorine has 9 protons. So if I look at the periodic table, then it has 9 protons, it's atomic number 9. And so in a neutral atom of fluorine, it also has 9 electrons. If this fluorine is near that sodium, and it gains this 1 electron, then now it's still going to have 9 protons because it's fluorine, but now it has 10 electrons. So if we think about our protons as a plus sign and our electrons as a minus sign, then that's going to give me a net charge of a -1. Now again, let's relate this back to our Bohr model of the atom. So here's my nucleus, here's the first shell, Here's my second shell. There's 2 and 1. Okay. The electron configuration for fluorine is 1s2, 2s2, right? Here's 2, 4. I have 5 more electrons, 2p5. So 2, 4, 5, that's 9 total. That gives me my 9 electrons. So to put those 9 electrons in, I have 2 here in the first shell, and then I have 3, 4, 5, 6, 7, 8, and 9. Now this looks just like my Lewis dot structure. 1, 2, 3, 4, 5, 6, 7. That outermost shell looks exactly like this. So here's my lone electron, here's my lone electron. Same with the sodium up here, right? With my 1 valence electron here, this looks like my Lewis dot structure with my 1 outermost electron. And this is the way that we're relating these together. So when I pick up an extra electron here, now I have a full valence. And so that full valence makes it happy, and it overall will give me an anion, which is called fluoride. This is the fluoride anion. And again, the charge as the superscript means that it's a -1 charge, and this is the way that works. Now if I transfer from my sodium to my fluorine like this, then I have a sodium that's a +1 and a fluorine that's a -1. And these charges are going to be attracted to each other because opposites attract. And that resulting charge attraction is going to give me an ionic bond. Okay, so the transfer of electrons from the sodium to the fluorine gave the fluorine a minus charge and the sodium a plus charge. And then that resulting charge differential, a positive on one and a negative on the other, can attract each other, and that will chemically bond them together. Okay, the way that I write this then is I have 1 sodium to 1 fluorine, and they balance each other out. Okay, sodium fluoride. And you'll see that it's a metal with a non-metal, and that's what you'll see in ionic bonds. Okay, so this is one way to use the Lewis dot structures, and you'll see a little more detail on those in my video on ionic bonds specifically, but this is just an introduction to how we're thinking about them and how we can use this model to understand bonding. So if you have questions on this, as always, let me know. Otherwise, I'll talk to you again soon.